This is an exam 4 review focusing on fluid pressure, which is one of the 4 units on your exam 4. And of course, it's also on the final exam. So we're just going to go through some principles of fluid pressure in this video. And then I'm going to work 3 different example problems, each in their own video, of a problem worked several different ways, using the resultant of the pressure distribution, using the F is equal to gamma Z bar A equation, and using horizontal and vertical if applicable. So again, a review of fluid pressure for exam 4, also for the final exam. Pressure at depth is equal to rho GH or gamma H. Gamma is a specific weight. It's in pounds per cubic foot, or it's in kilograms, it's in pounds per cubic foot, or in newtons per cubic meter. In the SI system, we have rho is equal to 1,000 kilograms per meter cubed, or sometimes you see it 1 megagram per cubic meter, but 1 megagram is the same thing as 1,000 kilograms, and that's a mass density. And so gamma is a specific weight, which is 9.81 times rho. And so if you take 9.81 times 1,000, you get 9810 newtons per cubic meter for gamma for fresh water. And this is a common number that we'll use. If it's possible that the fluid might be heavier than pure water, like for example, salt water or a drilling fluid or something like that, then you might be given a specific gravity of 1.1 or 1.05. And then you can multiply that 1.05 times 9810 to get the specific weight for your particular fluid. Or it could be an oil with a specific gravity of 0.9, 0.85. And so you can multiply that 0.9 or 0.85 times this to get the specific weight for a lighter fluid. In US units, specific weight gamma is 62.4 pound per cubic foot. Again, that's for fresh water. And so a real drilling fluid or seawater or salt water or some other liquid might be higher or might be slightly lower than that. So you need a gamma. And it's easy to just express pressure as gamma H. So flat plates, you've got plates that touch the surface or plates that reach a free surface. And so if the plate reaches a free surface, the pressure is 0 at that free surface, and then the pressure increases linearly with depth. And so you end up with a triangular distribution with a 0 pressure at the surface and a maximum pressure at depth, in this case gamma H. This is a vertical wall. This is a slanted wall. You still get a triangle, but now the length of the triangle is the length of that edge, whatever that is. But the pressure is a function of depth. It's not a function of the length of this edge. It's a function of depth. And FR acts a third of the way up on this triangle is where it acts. And the magnitude of H is equal to the area of the triangle, which is 1/2 base times height, times the width into the board. So it's easy to forget the width into the board, but pay attention to the problem and don't forget the width into the board. So these are flat plates that reach the surface. If you have flat plates that do not reach the surface, that exist at some depth, then the pressure at the top of that plate is a P1 that's equal to H1 times gamma. And the pressure at the lower edge of the plate is H2 times gamma. And you end up with a trapezoidal pressure distribution on that plate. And then, of course, it extends into the board, some width of the board. The plate can be tilted back like this. You still get a trapezoid, but now the pressure is acting upward on the plate. The magnitude of FR is the average pressure, which is P1 plus P2 over 2, times the length, times the width into the board, is FR. The location of FR is Y bar, and the official formula for a trapezoid is 1/3 2P1 plus P2 divided by P1 plus P2 times L. That's a good formula to have. Unfortunately, it's not on your crib sheet, but if you needed it, it's there. It should be in your notes. These are flat plates. So flat plates, you end up with triangles or trapezoids, whether they're at the surface or whether they're at depth. For curved surfaces, you can't use a simple triangle or trapezoid. And so you have to use the resultant force is equal to F horizontal plus F vertical. Sometimes people call this the composite method. And so if you had a curved dam here, the resultant force is the vector sum of F horizontal plus F vertical. The F horizontal is the force that would act on a vertical surface, which is the cross section, it's the vertical cross section of this curve. And so in this case, it's just a triangle. The F vertical is the weight of the fluid above this curve. And so you calculate the volume of this fluid. So it's this area times the depth times gamma is F vertical, which is the weight. If it's a quarter circle, then it's pi r squared over 4th is the area times the width into the board times gamma. And it acts at the centroid of a quarter circle, which is 4r over 3 pi. If you have a parabola, the area of this parabola is 2/3 base times height. And of course, times the width into the board gives you the volume times gamma. The centroid of a parabola like this is 3/8 b. You have the F horizontal. Of course, you have the F vertical, which is the weight. If you have a parabola that looks like this, it's called the spandrel. Then you have the same F horizontal, but now the F vertical is the volume of the weight of the volume of this fluid. And the area of the spandrel is 1/3 base times height times the width into the board times gamma. If you have a general curved surface that's below the water level, and you're looking for a force just on this curved surface, then the F horizontal is a trapezoid, but the weight above it is W1 plus W2. Later, we'll work an example like this. Center of pressure is a concept that sometimes is on exams just as a conceptual question. So the center of pressure is kind of a theoretical construct. It's basically the point at which the FR vector touches the wall. If you have a triangle, that point is basically in line with the centroid. If you have a trapezoid, the FR, the center of pressure where it touches the wall, is in line with the centroid here, which again is 1/3, what is it, trapezoid again? So 1/3 2p1 plus p2 divided by p1 plus p2 times L, which is less than halfway along this plate, that centroid there. So FR acts through that centroid and it touches the wall at that location as well. Finally, if you have a curved surface and you have F horizontal and an F vertical, the F horizontal and the F vertical intersect at this point. The resultant force acts through that point, but then it touches the wall here at P. And so this is the center of pressure. It's a point on the wall at which FR intersects the wall. So that's a brief review of the equations. I'm going to make several more videos where I work just some simple example problems.